let me introduce our speaker today for the second CIT seminar series. We have Dr. Rajib Ganguly here. He received his bachelor's degree from the University of Arizona, his PhD from Penn State University, went on to postdoc positions at the University of Wyoming in their active galactic nuclei group. There's also Johns Hopkins affiliation in there too. He's been a part of the University of Michigan-Flint since 2009. He's been the leader of our astrophysics research group that has been, supported and a part of Hubble Space Telescope and NASA. And during that time, he's brought along many students that have graduated, gone on to other positions now, maybe running portions of Flint and their science outreach events too. Today he's going to tell us a little bit about how experimentation and computational abilities over the last few years have dramatically changed how astronomy is done. A little rundown of what that means across the field and what that means specifically here in his research group at the University of Michigan-Flint. So with that, let's thank Dr. Ganguly. Can I sit down? You're the only one standing now.
Yes, that's me then. Fine. Sure. So with apologies to my physics comrades, sort of cycled title, which you guys have seen before in the previous talk, but it's a good title, so I'm sticking with it. I guess, but in keeping with Cam's precedent of putting in subtitles that may or may not be doom and gloom, I don't know. Best I could come up with was I can't do anything. So there we go. You might be wondering why an astronomer of all people is in a college of innovation and technology. That's a question I'm still pondering, but hopefully after the day, maybe it'll be a little, less opaque as to what I'm doing here. As with any talk, behooves me to give proper credit where credit is due. I can't take all of it. I wouldn't want to, but these are some of the various people who have contributed to the things that I'll be talking about today. A couple of special shout outs, one for Danny Abdul-Kazam and Brianna Kristen, who are helping me now with what I am doing. So this is an important talk so that they know what they're actually supposed to be doing. And also an extra special shout out to Allie, who showed up and helped me fight with this thing. So the technology part is out for me, so I'm left with doing College of Innovation and stuff, I hope. All right, so most of the beginning of this talk, actually all the beginning of this talk, is going to be background information, since I am the only astronomer in the room, I think. Well, maybe Patrick. Yeah, okay, yeah. So I think it behooves us to get everyone up to speed with what I will be talking about. So in terms of background, the first place I'd like to start is here. And I should warn you, this being a physics talk, it's hard to do any physics without showing any equations. So I've gotten it down to 3. Okay, so hopefully that'll be okay. 2 of them are going to be on this slide, and one is just a consequence of the first. So hopefully it won't be too bad. But this is a graph of what's called the M sigma relationship. And this is a relationship that's been established over the past few decades of work, where on the vertical axis, we are plotting the mass of a black hole that resides at the center of a galaxy. And notice the scale on that vertical scale goes from 10 to the 6 all the way up to 10 to the 10. So down here, let's do this so the online folks can see. So down here is 10 to the 6, and up here is 10 to the 10. The units here are in terms of the mass of the sun. That's that's the standard thing to do in astronomy, was to refer to just the mass of the sun. So these are things that are millions to tens of billions times the mass of our own sun, which is hard to fathom, especially when you think about how do we form these things, we grow these things, and that will be the subject of the next slide. On the horizontal axis is, well, m sigma, it's sigma. What is sigma? It's a velocity dispersion. So you take a spectrum of the galaxy and you ask, okay, how fast are the stars going in that galaxy? So the spectrum has encoded in it velocity information, so you can actually measure what is the velocity width of the stars going either randomly going around or maybe rotating around the galaxy. How fast is that? And so the numbers there go from like 60 kilometers per second down here. On this end is 400 kilometers per second. Sort of keep in mind, hundreds of kilometers per second as sort of a typical value here. And what you want to notice here is that, yeah, it's a correlation. I mean, they're scattered, sure, but there's no points up here. There are no points over here. Okay, there is a correlation between those two things. Now you might think, well, yeah, if you have a bigger black hole, you gotta have things going faster around it. So in order to stay going around it instead of falling in. Well, that doesn't quite hold water in this case. And the reason it does is a question of scale. So the scale over which the velocity dispersion was measured is much, much bigger than what the black hole has influence over. So here's the two equations. So if we look at sort of gravity from the black hole and compare it to the energy in those stars as they're moving around, we can ask, okay, out to what distance could the black hole actually influence those stars? And the answer in this case for some fiducial values of 10 to the 8 solar masses and 200 kilometers per second, that's right there. The answer is it's about 10.75 parsecs, which is just under what the William Falcon did in the Kessel Run, right? That was 12 parsecs. That was, remember, a parsec is not a unit of time, it's a unit of distance. George Lucas wrote that. All astronomers went, oh God, forever we're gonna have to be fixing that. But yes, it's a distance. Just for reference, the star that's closest to the sun, just Proxima Centauri, is at 1.3 parsecs. So that just gives you hopefully a sense of scale. So about 10 times that is what a 10 to the 8 solar mass black hole would be able to influence in a galaxy like the Milky Way. Which is not that far. We, by the way, are roughly 8,000 parsecs from the center of the galaxy. So the black hole at the center of our galaxy has no influence whatsoever on us. Okay. So then that brings up the question, okay, why is there a correlation there? Those two things cannot be causally related. So remember, correlation does not mean causation. Okay. And in this case, there is no physical mechanism by which we can have those two things be causally related. So rather, this is a suggestion that those two things both depend on something else that manifests in this correlation. And that thing, well, that thing is understanding how those two things come about. And the correlation suggests that if we can learn about one, that gives us clues at least about how the other works. And so for my end, I'm interested in, well, how do black holes get their mass? And if I can figure that out, then we can shed some light on, okay, how do galaxies evolve? And that's an important thing in trying to construct what the history of the universe is. All right, so let's talk a little bit about how black holes come about. So mentioned before, that these things 10 to the 6 solar masses or 10 to the 10 solar masses, it is hard to fathom that these things can be born like that. They can't. In the regular ways normal ways that we think about forming black holes as the one of the end products of stellar evolution, well, you have to start with a star has more mass than the resulting black hole. You can't have more mass than what you started out with. They don't really eat stuff like babies do. So rather, these are things that have to be grown instead of being born that way. They have to be grown up to that kind of mass. Okay, and so there's a couple of different channels, and this is a nice figure by Jenny Green, where she's looking at, hey, there's possibilities of the seeds of this growth being from direct collapse of some large amount of mass. Maybe we can see things up to, the word here is 10 to the 4 solar masses, so 10,000 solar masses, which is a far cry from 10 to the 8. Over here, we can think about the deaths of massive stars, which is what I just talked about. And there you get on the order of hundreds of solar masses. Okay, so a far cry, regardless of which one you think it is. And she's actually suggesting here, some observations of the very high redshift universe, so we can try and see these things. And that's very exciting work that's going on with James Webb right now. But it's not in the scope of my talk. Rather, I want to look at the thing that's in common with both of these things. So regardless of which way you want to seed those black holes, you have to grow them. And it's the growth that's interesting. Okay. Now there's two ways essentially to grow black holes. One way is you take two black holes and you merge them together, you make a bigger one. Okay, so that's mergers. We are just starting to look at gravity waves, which are revealing more and more of these kinds of systems to us, where we can actually study them, and those are great. The other way is by actually having them accrete matter in a slow, prolonged way. And in this case, slow means that they're devouring roughly a sun every year. And in terms of the time scale, we'll talk about time scale in a moment when we get to demographics. So let me save that question. All right, so the next question is, okay, you want to look at these systems that are where the black hole is actually growing. It's actually feeding on things. So how do you find them? Well, here's an example of how not to find them, which is look at images. So here's images of two galaxies. These are both lovely Hubble pictures, okay, of two spiral galaxies. One of those spiral galaxies, they both have black holes in their center. They're both massive. One of the black holes in one of those galaxies is actually eating stuff right now, as we see it. The other isn't. I don't know about you, but I see nothing in that image to tell me, let me distinguish which one is doing what. Okay. So imaging these things is not the way to go. So imaging is what we call morphology, so we can look at shapes of things. And when we look at galaxies, we have roughly 3 different kinds of shapes. We have ellipticals, we have spirals, which is what I showed you. We also have amorphous things, irregular, and there's all sorts of subdivisions there, but we can't use any of that to tell us whether a galaxy is actually a black hole at the center of a galaxy is actually feeding on stuff or not. So what's the other choice? The other choice is we look at spectra. So most of the talk will be concerned about spectra and looking at spectra and interpreting spectra. When we look at the spectra of galaxies, they roughly divide into two basic types. One, where the black hole is not doing much of anything. That's what we call a quiescent galaxy. And the other, which is where the black hole is actually doing something, and that's called an active galaxy. And within the active galaxy part, we have a host of other, sub-classifications. I'm not gonna bother with any of them. I will probably just say active galaxies, or if I'm lazy, I'll just say quasars. But you see some percentages there. So 99% of galaxies that we see in the universe are quiescent. It's only 1% that actually we observe to be actively accreting things. Okay. That gives us a hint, a clue, as to what's the duty cycle. So when these things are eating a solar mass every year, how long does that happen? So if we take what we see as a snapshot in time, well, 1% means, okay, 1% of the galaxies are eating now. What's the duty cycle? Well, the age of the universe is something like 13.6 billion years. 1% of that is on the order of 100 million years. So that's what's called the saltpeter time. That's roughly the duty cycle that we're thinking about. How long does it take to grow things? So around 10 to the 8 years. And you think, okay, 1 solar mass per year for 10 to the 8 years. Yeah, that'll get you up to 10 to the 8 solar masses. So that kind of, that's consistent. Okay. Back of the envelope calculations are fun, but of course, devil is in the details. So we'll get more into that as we go forward. All right, so spectrum. Let me show you what the spectrum of a quiescent galaxy looks like in comparison to the spectrum of an active galaxy. So that looks like this. So what we're seeing here is, flux or flux of light, how much light you're getting on the vertical axis, some arbitrary units, it doesn't matter. And on the horizontal axis, we're seeing the wavelength of the light. We could alternatively talk about the frequency of the light, or the energy of the light on the horizontal axis. Those would be equivalent. But in this case, we're doing rest wavelength. Okay. And the scale there, the units are in angstroms. It goes from 3,000 on one side to 8,000 on the other side. 10 angstroms is 1 nanometer for those of you who are SI buffs. So it's 300 to 800 nanometers. Okay. What we see here for a quiescent galaxy, the light that we get from a quiescent galaxy is just from the stars in that galaxy. So the spectrum of a quiescent galaxy is really just a spectrum of all the stars put together. And what you notice is that there's a sort of very generic shape where it increases as you go toward the ultraviolet. So the ultraviolet sort of starts somewhere here. This is all the visible part of the spectrum. So it increases, in the same way that anything with a characteristic temperature would, and then it tanks. Okay. What you also see here is these little dips. Those are called absorption lines. Those are places where the atmospheres of stars are actually absorbing light. Okay. So we see the atmosphere silhouetted against the core of the star. We see this in the sun as well. Okay. On the other hand, this is a spectrum of an active galaxy, one where the black hole is actively eating stuff. So first of all, I want you to notice that, hey, this spectrum, it just keeps going up and up and up. It doesn't tank, doesn't fold over. Second thing I want you to notice is that everywhere where there was an absorption line in the quiescent galaxy, there is now a spike, not a dip. So a spike, that's an emission line. Okay. So specific atoms are emitting light at those specific wavelengths. Okay. I'm gonna give you another view of this kind of a spectrum. I'm gonna extend this a little farther into the ultraviolet so we can see. Okay. And so going from here to here, that's what we were showing before. And now I actually have labels for the different emission lines. Okay. So this one over here, this is a commonly used one, even in amateur astronomy circles. This is what's called the H alpha line. So this is a transition in hydrogen. It's the n equals 3 to n equals 2 line for you chemists out there. This is at 656 nanometers. Amateur astronomers like this line because they can use that as a filter to image the sun. And so they're not, letting in gobs of light in, they're just letting in that one wavelength and you get really good images that way. So that's H alpha. This is another one, H beta, H gamma. There's these other things too. There's a helium there, there's a magnesium there. Okay, there's an aluminum there, and oxygen there. There's these Roman numerals next to them, which indicate a spectroscopy notation. Okay, so a Roman numeral 1 means that that line is from the first spectrum of helium, which is the neutral helium. Magnesium with a Roman numeral 2, that's from the second spectrum of magnesium, which is singly ionized magnesium. So whenever you see a Roman numeral there, just sort of transplant in your head that, oh, Mg2, that means Mg plus in terms of the ion. Okay, when you see oxygen 3 here, that's oxygen 2 plus as an ion. So we can actually pinpoint what ions are doing the emitting. I'm gonna continue this, show you that this is gonna keep going. Oh, let me, yeah, a couple of notes. So just to note that there's an underlying spectrum on top of which the emission lines are adding, okay? And that's what we call a continuous spectrum. Okay? It's not a thermal spectrum, so it doesn't fold over like a thermal spectrum would. Okay, this is non-thermal. There's also these emission lines, and these emission lines, let me say something about how broad they are. So remember we said that in a galaxy, a quasi galaxy, we just have the stars. Stars have velocity dispersions of something like a few hundred kilometers per second from the M sigma relationship. These emission lines have widths on the order of tens of thousands of kilometers per second. So 2 orders of magnitude larger and coming from somewhere that's a lot more compact. Okay, so like a few parsecs. Which then tells you that, oh yeah, there has to be a very massive object involved here. And that's early on how we figured out, oh yeah, and deduced that, yeah, these are supermassive black holes that are powering these things. It has to be. All right, so I'm going to continue this spectrum farther into the ultraviolet towards shorter wavelengths. Okay. And you see here more labels with ever increasing Roman numerals attached to them. So there's a carbon 4, which is carbon 3 plus, silicon 4 is silicon 3 plus. On the extreme end is oxygen 6, which is oxygen 5 plus. So you've taken 5 electrons away from that oxygen. That's taken quite a bit of energy to do that. But these are ions. Okay, they're all ions. This is all plasma stuff. Okay. What I want you to see here is that continuous spectrum continues. All right, it's still not tanking. It's not going down. We are starting to see more highly ionized species. Okay. I put this here because the next slide is going to throw us for a huge loop. Because in some cases, I mean, active galaxies are already just 1% of all galaxies. Well, in roughly 10% of active galaxies, we see things like this, which really throw us for a loop in terms of interpreting what's going on there. Let me overlay these two so we can have a better stab of what's going on. So there's a continuum. Okay, there's emission lines being superposed on the adding to that. But in addition to that, there's also gas that is absorbing the light. Okay. And I want you to notice the pattern of absorption is the same as the pattern of emission. In other words, the ions that are doing the absorbing are the same kind of ions as the ones that are doing the emitting. And what is happening is that there is a Doppler shift going on. So when we look at, let's pick on on this guy, carbon 3 plus, carbon 4. So there's the emission line from carbon 4. But then there's also gas that's being silhouetted and is absorbing gas at all these wavelengths. And the reason it's a variety of wavelengths and not just one specific wavelength is because there's a blue shift. Because that gas that's doing the absorbing is coming at us relative to where the quasar is. Okay. So that is blue shifted absorption. On the rare occasion that I get to teach astronomy 120, this is the point where I challenge my students to say, okay, so you have something that's giving you a continuous spectrum that's not thermal. You have something that's giving you emission lines. And we go over what kinds of things can do that. It means it has to be a hot, dense source that gives you continuum. In order to have emission lines, you have to have a hot, low density medium. You also have these absorption lines in 10% of the cases, where you have to have, again, low density, but cool gas, cooler gas, silhouetted against hotter stuff behind it. Draw me a picture of what possible scenario could give us that kind of demographics. And I give them about 5 minutes, and I watch them struggle. And then I point out to them that, you know, as much as you're struggling, just think that scientists not only have to be creative enough to come up with a situation that could work, we have to come up with every situation that could possibly work. And then we have to go and parse those possibilities and figure out additional things that we could use to distinguish between them and rule things out. So science is inherently a very, very creative process. It has to, just like Einstein does. So what's the scenario that we've sort of come down upon? Okay, well, I'll show you some cartoons. The first one is going to be one that's favored in the greater Boston area, centered on Harvard University, which is where the graphic comes from. So in this cartoon, what you're seeing is there's a supermassive black hole at the center there, and that's the driver of this whole thing. The continuous radiation that you see comes from a disk of material that's in orbit and slowly spiraling into the black hole. So that's an accretion disk. Okay, that's how it's growing. Note that there's a gradient of color there. That's supposed to indicate a gradient of temperature. So every annulus of that disk is emitting like it has a particular temperature, but when you add them all together, that's what gives you the non-thermal spectrum. But that's a disk that has to be opaque. Okay, it has to be a hot, dense source to give us that continuous radiation. On top of that, we have this red thing, which is this flow of material that's coming off the disk and in some fashion being driven away, accelerated in some form. Okay, that acceleration, of course, it has to overcome the gravity from the black hole. So that's got to be an incredible force that's pushing out. Okay, but that's a scenario. What happens here is that, hey, on the part of the gas, part of it that's just come off the disk, it still has a temperature that's, you know, similar to what it had coming off the disk. But then as it goes farther away, it cools off. This is the source of the emission lines, the low density hot gas that we need. And then in some cases, if you see this gas silhouetted against all this, that's where you see this stuff producing absorption. That's a scenario that we've come up with that's sort of survived all the scrutiny so far. So we'll see. All right. This is what we've learned just from examining the ultraviolet and optical part of the spectrum. But of course, there are many more parts of the spectrum than just those two wavelengths. We have radio, we have infrared, we have X-rays on the other side. That's the entire electromagnetic spectrum. And the really interesting thing about these active galaxies is that they emit in all bands across the entire electromagnetic spectrum. Stars don't really do that. Like the sun, it doesn't really do much in the infrared, right? It doesn't do much in radio. Okay? It doesn't do much in X-ray. It's sort of this nice black body that peaks at like 6,000 Kelvin. And that's good. That's good for us. But anyway, these things actually do. And we learn different things about these monsters, depending on which band we are paying attention to. Okay? And the question, of course, then becomes, okay, what components do you actually need in order to be able to explain the breadth of information that you were getting from this? And that's what the next portion of this introduction is going to tell you. So I'm going to start with the X-rays, and then we're going to go toward longer wavelengths. Okay. So this, by the way, this is another spectrum. So you're just seeing relative intensity here. Notice that there's many decades plotted here. It's a log plot. And then here, this is frequency instead of wavelength. Wavelength goes in that direction. So radio has longer wavelengths than X-rays. All right, I'm going to start with the X-rays. So that disk, the inner portions of the disk, tend to do a decent job of producing low energy X-rays, which is a weird word, the phrase to think about. Low energy X-rays. It cannot produce high energy X-rays. So there must be something else. Well, folks working in that regime think that, oh, like the sun has a corona around it, that's this hot thing. Well, maybe there's a corona around these accretion disks. And that's what produces these hard X-rays, these very high energy X-rays. That's a component that's needed. The infrared. Well, the infrared is dominated by emission from molecules, which is really, really strange. Because, as I said, we have ions going on here. We have things like oxygen 5+. That's not a situation or an environment where molecules can survive. They get dissociated much more easily. So the fact that we see molecules means that there has to be another component that's farther away, where it can be cool enough for molecules to actually survive. And from demographics of things, we think that takes the shape of some kind of a donut around it. We don't know exactly what the geometry of the donut is. It's a torus of some form. It might be just an extension of the disk as you get past the where the molecules can actually survive. Maybe there's some changes in structure. It could be that. Okay, but there has to be something there. And none of this explains radio. The radio, actually, we're actually fortunate with the radio, because the radio, we have a better handle. It comes from a jet. And we know it's a jet because we see the jet. Let me move over here. So this is over here a picture of an entire galaxy. This is Centaurus A. Okay. And overlaid on that image is a radio image. And what we see here is these are the jets that we're talking about. And they're going sort of perpendicular to Cen A. Okay. The scale here the size scale is huge. And remember, this is the size, this is on the order of the size of the entire galaxy, which is well beyond what the black hole could even possibly influence. But the fact that this is such a tight thing over such a large scale means that it has to be extremely highly collimated. You know, like turning on a hose and putting your thumb on the end to really make it come out just one small area. It really gets collimated, can go really far. Okay, so that's kind of what we think is happening here. It's a jet, okay? A jet like this, and it originates from very close in. So, with all these clues, we have now the arduous task of asking, okay, with those clues, we think those are the important components that we need. What are the fundamental parameters? So things like black hole mass, things like the spin of the black hole, things like, oh, what's the orientation of this thing since it's not a spherically symmetric thing? How are you looking at it? What's the rate at which gas is falling into the black hole? Okay. Maybe those are fundamental parameters. Okay. And on the other side, nature takes all that and does what it does and produces the spectrum that we see. That has this continuum, it has these emission lines, has these absorption lines. And of course, what is in between is all the detailed, interesting physics. Physics of disks and jets and outflows. So that's my broad introduction now. From here on out, I'm going to be talking specifically about outflows. That's my bread and butter. And I'm going to be talking about them in the context of studying them with absorption lines. So using gas that's silhouette against the background and being able to tell lots of interesting things about the outflows themselves. So let me give you another view of the outflows themselves. So you saw the Harvard-centric version. Let's come back to this picture. This is another picture of another galaxy. Okay. At the center of that galaxy, maybe there's a black hole. So that's right here in the red outline here. And what's shown here is schematically a cross-section of what an accretion disk might look like in terms of what shape it might be, under certain assumptions. Let's give you a sense of scale here. So for a 5 times 10 to the 7, that's 50 million times the mass of the sun, black hole, the size of the black hole fills Earth's orbit around the sun. So that's how big a 50 million solar mass black hole is. Incidentally, the galaxy itself is several million times that size. There's this inner edge of the disk, where there's a gap between where the event horizon is and where the disk ends. Okay. That's about 3 times that size. So in our context here, if this is a 50 million solar mass black hole, that would be roughly the orbit of the asteroid belt in our solar system. So that's how far it is. There's a gap in between because general relativity says so. There are no stable orbits that occur in the in-between region. And if you want to know why, you have to ask James. He's the one to tell
We have a sheet somewhere.
you. I'll let him work. All right. The orbit of Neptune, by the way, the largest big planet, is somewhere out there. What I'm going to show you right now is a simulation, a hydrodynamic simulation. So this is computational fluid dynamics, something that some of our engineering colleagues do. But in this case, this is being done at the very, very high extreme Reynolds number limit because these are viscousness flows. This is all plasmas. And what they're showing here is, hey, they've taken this disk that has this shape and they've assumed that. And they're asking, okay, how can we drive material out? And what shape does it have? What does it look like? So it looks kind of turbulent, at least in this particular realization. And I want to seed that here. It doesn't really have the shape that the Harvard folks wanted, where it's getting pushed up and then turns over to be an outflow. It's actually just going straight out. It's pretty that. But that's an idea. And that's one of the many things that I eventually like to get my hands on, doing some hydrodynamics simulations, but we're taking baby steps to get there. So that's a picture. Let me turn to the other side, which is data. And this is where I want to convince you that astronomy is inherently a big data science. What I'm showing you here is spectra again. On the horizontal axis, you see rest wavelength. Every row of this graph is showing you one particular object. And well, let me see. Let's rest wavelength down there. Let me go and color code these back with the color coding that we had before, with the red on the radio side and then the blue on the other side with the X-rays. Okay, so that's the same color coding. Okay. So every row in this thing is representing one object, one black hole, one system that's accreting around a black hole. That graph goes up to about 130, but that's only because I cut it off. This axis goes up to 54,000 with a particular sample that I'm working on now that Brianna has to contend with. You can ask her. She's working over here in the radio. That's her job. That's her. That's what she's doing. Each row is a particular object. There's a third axis here, which I want to point out. That's how much power is being given off. So that spectrum that we showed before, it is the third dimension here, like this. And it's being represented in this plot by how bright the particular pixel is. So every single pixel that is featured in this graph is a data point for 54,000 objects and however many data points there are for each wavelength that we have. That's the data set that we're working on. And that's a huge, that's not a big data set. That's a huge data set. I'm sorry. It's too much. I'll allude to that a little later on too. Okay, good. So I want to come back and focus on this part, which is in the ultraviolet. So that's my baby. Where I showed you this graph before, okay, and the green outline is telling you, okay, that's where that particular thing is coming from. So studying outflows using absorption. So again, this is that dramatic example with these outflows that you see in absorption here. There's a few ways that we can actually study them. We can actually go system by system and actually examine exactly what interesting details there are. And I'll show you an example of that on the next slide. And then we can also look at statistical properties, like by identifying whole ensembles of things, populations, and trying to understand how do these things correlate with different properties of the black holes. So that's where we're going next. For one particular example, if we're looking at just an example of an individual system, here's one where we have Hubble Space Telescope data from. Okay, this is just the part of the spectrum that's right here. This is the H1 plus N5. So that's nitrogen 4 plus and Lyman alpha. So here's the H1 Lyman alpha line, and here is the nitrogen 4 plus. Okay. Now nitrogen 4 plus is a lithium-like ion. When the valence electron goes from the 2s state to the 2p state, it does so with a doublet. Those of you in modern can tell me why that is. Okay. I'll test you later. Okay, but it's a doublet, right? What's shown in cyan there is absorption by hydrogen, so neutral hydrogen, H1. What's shown in yellow is that nitrogen 5 doublet. It's absorption in that doublet. This is where we're getting the third equation. No more equations after this, okay? We can take the wavelength scale and compare it to each of these particular wavelengths and actually transform the wavelength scale into a velocity scale for each wave, each species, each transition. And we can line those up in velocity. And if we do that, it's like magic. We can see, hey, you know what? There's a particular velocity here. So this is the velocity down here. There's a particular velocity where we see absorption by H1. We see absorption here by, this is silicon 2 plus, silicon 3. We see absorption here and here by the two members of the nitrogen 5 doublet and 4 plus. And they're all there. And so we can use that as to take detailed measurements of, okay, how much H1 is there? How much silicon 3 is there? How much nitrogen 5 is there? And when we do that, then we can also ask the question, okay, what are the conditions that we need to have in this gas that gives us those relative abundances of those different ions? Okay. And that's some of the physics that we can really do. The other thing that I'm going to point out is that it's not just one thing that's doing absorbing. You can actually count with your eyes. There's one right there. There's one right there. There's one right there. You can just place them and read off what the velocities are. So there's a bunch of them, all within 1,000 kilometers per second of each other. We're going to come back to that later. All right, let me turn the page and go back to think about ensembles. So when you don't have this kind of quality data, and we generally don't, it's expensive to get, we have to rely on other means to try and distinguish. Is it outflows or is it something else? Okay. So in this graph, what I'm showing you on the vertical axis is what is the velocity width of an absorption line that we see? Okay, and in this case, we're looking only at absorption by carbon 3 plus. That's what's on the lower left-hand corner. It's also lithium-like ion, has a doublet the same way nitrogen 5 does. Oh, and on the horizontal axis, I'm asking, okay, from the Doppler shift again, how far is it? What's the velocity relative to where the black hole is? So, going out this way, that means that's how fast it's coming toward us. So it's just a line of sight velocity. Okay. Now, there's these three colors up there, and those are just colors that are historical in nature. The blue ones are what are called broad absorption lines. So they have the ones that have the widest troughs, okay, largest delta V. Okay, and here's an example of one of those. So here's the carbon 4 emission line. This is that nitrogen 5 and Lyman alpha emission line that we were looking at before on the previous slide. Okay, and you can see that there's a whopping trough there, and the scale of that is, you know, something like 5,000 kilometers per second. That's scale here is in thousands of kilometers per second, which I guess is a megameter per second. So that's these things. So historically, in days where they didn't have the technology, they made this arbitrary cutoff at 2,000 kilometers per second. And they said, okay, anything above that, we know that has to be an outflow. It can't be anything else. We know of nothing else. I mean, if we could have a galaxy in the way in our view of the quasar that imprints some absorption lines too. But remember that the velocity dispersion of a galaxy is just a few hundred kilometers per second. You cannot get, several thousands of kilometers per second. There's no way. So those things are very clearly outflows. I would argue that these are also outflows, and I'll show you why in a moment. The ones down here on this lower end, those are what are called narrow absorption lines. So this is an example of that. So you see how narrow this is here compared to that. That's very broad. This is pretty narrow. These are things that are, a few hundred kilometers per second. We might have an issue with those in terms of being able to distinguish, are they due to interloping stuff or are they actually part of the outflow? And then there's these things in the middle, which historically everyone ignored until we actually had technology to pay attention to them. And when we finally did, we didn't know what to call them because they weren't broad absorption lines the way we thought of those. They weren't narrow absorption lines the way we thought of those. So the name that stuck was mini BAL, so mini broad absorption lines, as opposed to maxi narrow absorption lines. That's what stuck. If I look at, and here's an example of setting these outflows, if I look at just spinning up a histogram of the velocity weights, you see that there's no physical thing going on that separates, these guys from these guys. It's just a continuous thing. Whereas here looks like there's a dearth right here that separates what's narrow from what's, well, not narrow, I guess, broad or mini broad. Okay. This I will argue actually is possibly due to a computational artifact. The carbon-4 absorption line, the two members of that doublet, if you use the Doppler shift formula, that separation corresponds to 500 kilometers per second. So those two members of the doublet are separated by 500 kilometers per second. As you get wider and wider and wider, they start blending together. And at some point, a computer is going to have a hard time being able to separate, that you have a doublet. Okay, so that's what I think is happening here. So 500 kilometers per second is right here. So you can see there's this valley of points, a dearth of points there. Now that's from just binning up one axis. What about the other axis? So I'm just going to take these guys, the narrow absorption lines, and bin them up in terms of velocity. And we see something really interesting there too. And that is, there's this interesting shape here, which at large velocities, this shape is completely consistent with randomly situated stuff between us and the quasar. Things that don't care about what the quasar is doing, where it is, what's happening. Okay, that's all consistent with stuff that has no relationship whatsoever with the quasar. That's things like galaxies in between, cosmic web is in between. So that's cool. That's nice. We can use this tool to study those things, and people are doing that too. In here, though, at smaller velocities, you see that there's this huge excess over what you would expect from a random population. Okay. Those are the things that I'm interested in here that are actually correlated with the quasar. So those are things that we call associated absorption lines, just to continue the nomenclature here and make it more confusing. So the thing that we want to focus on is this outline here. Those are the things that are out. Maybe with some small contamination, but otherwise, for the most part, outflows. And that's great. We can see them. Let me turn to one example of what we can do, having identified an ensemble like this. And this comes from work that's was done pushing the end of the last century, and published at the beginning of the century, in the form of my dissertation. So back then, a large sample was 64 objects, not 54,000, but 60. We've come a long way since then. But at that time, I had an ensemble of objects, and these were derived from what observations that were available in the Hubble Space Telescope archive. And I was able to go and use the spectra to actually go and identify, okay, these are objects that have outflows. These are ones where we're not seeing the outflow in absorption. And then I went and started compiling properties of the quasars themselves, of the active galaxies. First, I started with, well, what's the radio doing? So this RQ and RL, it's radio loud and radio quiet. So that's radio. And then I looked at, okay, what's the shape of the radio spectrum? Is it steep? Is it flat? I looked at X-rays. SX means soft X-rays, so that's the low energy X-rays. Is it normal? Is it weak? And I looked at what is the shape of the carbon-4 emission line? Is it broad? Is it narrow? What? And I took all these different measurements, and I did what's now called a hierarchical clustering analysis, or a k-means analysis, where I basically take those as dimensions in this higher dimensional space, and I ask, okay, how far from each other is each of my objects? So how similar are they? And of course, the ones that are most similar, this is the one that's most similar. So they have the shortest distance between them. Looking at the whole population of objects here, the first separation is based on radio, and then we have these other ones. What I want you to notice here is something that astounded us, which was all the ones that red stars. Those are the ones that have outflows that we were measuring in absorption. Where are the purple ones? The purple ones have none whatsoever. And that's even the largest subset, I mean, in terms of statistical significance. And that was quite shocking. So that resulted in a thesis. So we had the absence of AALs in flat spectrum, radio loud quasars with mediocre carbon-4 emission. All right, that's cool. Yeah, we'll make a list of the last thing. So that was a dissertation. That's one example of doing big data science. I'd love to do that again now with 54,000 objects. See, but now this will be the last thing I show, I guess, is probably what is my most famous plot that I've made. People still, I went to a conference this past summer, and they were still citing this, which is amazing considering this was in 2008. Nobody's done better. So what I did is I went to different catalogs that were all finding different kinds of outflows. And I said, okay, you know what? Let's compile all these. And let's also look at what are the luminosities? What's the power coming out in terms of light from these objects? Okay, and the power here, it's in log units. So there's a log. It's in ergs per second, which is in CGS, which is God's units. If you need to use watts, then just subtract 7. So it's 10 to the 40 watts, and this is 10 to the 36 watts, okay? What I want you to notice here is that there are no points here. Nothing. So what we're plotting here is what is the velocity and what is the power in light. Okay? There's nothing here, absolutely nothing. This green curve here is not a fit. It's just plotting velocity goes as luminosity to the 2/3 power based on some theoretical arguments. That's not a fit, and it works remarkably well. I mean, there's a little bit of scatter, right? There's some points there, fine. But by and large, the velocity of an outflow is capped by the luminosity of the source. That is a telltale sign that it is photons that are driving these outflows. And that's one of the remarkable conclusions that we've had in the last couple decades, that it is radiation pressure, pressure from photons pushing on this gas. Then that's what's doing the accelerating. That's what that simulation did that I showed you before. Now, you notice that there's all velocities below a cap that are allowed. Yeah, and there's a few reasons for that that's possible. It is an envelope. One is that velocities have this notorious habit of being vector quantities, much of the bane of 143 students. So if you have a velocity vector that goes that way, well, what are you going to measure? Well, you're going to measure just a component that's coming toward you. So there's a cosine of an angle that's involved. Okay, so that could be, a reason why you see this thing. You could have questions about how efficient is that radiant driving. Maybe there are other processes that sort of get in the way, and that's one of the big things that we have that we're going to be doing, that we're looking at so far. All right. Since I'm already past time, I'm going to skip to this. In conclusion, we have a black hole, and we have one in every massive galaxy. And that black hole is a diva. And in this case, what that means is it is a supermassive beast, meaning it's millions to billions to tens of billions times the mass of our own sun, which means they cannot come from just the death of stars. They have to be grown that way. Understanding how they grow is going to require, looking across the entire electromagnetic spectrum, because there's information about these things that's given in each of those areas. The ultraviolet and the X-ray, we can study the inner regions. Infrared, we can look at this enshrouding torus. Radio, we can look at the jets, okay? And we can decipher different components that we might need, okay, in different combinations. And you can pay attention to that with PICER coming in. And devils in the details, if you look at these things with high resolution, you can see that, there are discrete clumps from that one example that I showed you from Hubble. Okay. So these outflows, they might not be just these laminar smooth things. There might be turbulence going on. There might be, clumpiness going on. So that's sort of where we stand right now. That's where we're going. It's very exciting. But thank you very much for listening.
Is there any questions for Dr. The one that popped into my head real fast, is there any argument on like a fundamental argument as to how you get that L to the 2/3 power? Or does it exist in heuristics?
There is.
That's another
I'll
talk.
leave it at that. Yeah. Let's say that's another talk. Sure.
Yeah.
We'll go with that.
No.
So, thank you so much, Rajib.
Yeah.
So how people estimate the total mass of like a black hole? Or like you measure it in terms of solar mass?
Yeah.
So is that like a based on imaging, or like how they can estimate?
Let me go back to. Let's go back to this. So the way to do this is you look at these emission bands, and we know what the size of those things is. Well, let me go back. The way they do it here is you look at this and you say, okay, I can measure the velocity with it. Okay. With repeated observations, we could actually figure out what is the size of the region that's doing the emitting. So if you have a size and you have a velocity, and that gives you a mass. Does So GM over R equals V squared. Or V squared.
So the size will be determined based on the wavelength?
No, the size is determined by having repeated observations. What happens is that you see these things, revert, let's say that. What happens is that these things are variable. So you see, what you observe is that, okay, the continuum, changes a bit. And then sometime later, in response to that, the emission lines respond. And by measuring that time delay, that gives you a size. So C times that time delay is the size. So that's how far the gas was before it came to C, before it came.
So let's assume I can order from my basic, and
Yeah.
sorry for my ignorance.
No.
So a mass have to be related to a volume and density, right? To be able to characterize.
Well, you need a velocity and you need a distance.
Velocity and distance.
Yep.
And then how the velocity will help to determine a mass.
I apologize, I write another equation. So if we start with Newton's law of gravity, you have G M over R squared. And we have circular motion, right? So if we have a centripetal force, that's M V squared over R. All you need is, to get M, all you need is a V and an R. So if you know how fast the gas is going and you know how far it is from the black hole, you can
And the
estimate.
G is just the universal gas constant.
No, not the gas constant, it's the gravity, yeah.
Yeah. So another question, if you get in mind. For the fluid dynamics part,
Mhm.
so you mentioned this would be for extremely high Reynolds number, right?
Yes,
So-
this is a,
Right.
because there's no viscosity.
Right. So it's almost going to be like absolute invasive type of simulations. But then I know that this is going to be extremely hard to be able to simulate for the limit of high Reynolds number, right? In terms of the computational or discretization and so on. So how, and also the background, because my understanding in astrophysics, they look at the problem as in-body problems rather than continuum simulations.
Well, the
So
one I
it's
showed
just
you
like
was
you
the
have-
continuum
yeah.
simulation.
Mhm.
That was actually a hydrodynamic simulation. That
Just
was-
like
that was
pure
full blown.
continuum simulations. And then how, like, the size, like when the computational domain, like how it looks like, or also the boundary condition.
So for this one here. To go back and read his paper. Explain. So. I don't remember the specifics of what the precision was, what the grid was. But in terms of the domain, I mean, it's the domain is exactly what I described here. It's going from right here, the inner edge of the, not the inner, quite the inner edge of this, but out here. To, actually sort of orbit of Neptune kind of.
But the color scheme here, this is the velocity, right?
The color scheme is actually indicating density
Yes.
in this case.
So
In this image.
then the simulation is not just the hydrodynamics, right? You also have the energy. So the
Oh,
simulation.
sure, yeah, they have it all, yeah. Cool.
Towards the end of your talk, you
Yeah.
mentioned this K-means clustering. That was actually unsupervised machine learning. So that was a very popular methodology for physicists back at the beginning of this century. I was just curious.
So when I did it, I was probably maybe the second person in the field
Okay.
who ever did something like that. The first person who did my field was the postdoc I was working with at the time.
That's great to see that.
Yeah.
Stuff was even helping physicists, that. Great, thank you.
Yeah, I'd love to get back to that, doing this with 54,000 objects instead of 62.
Is it right to doing that now? So you got 54,000 objects and use the same groupings that you had?
Cam will tell me.
Yeah. So, how many parameters did you have? Like there was the carbon floor, I mean, it was like the narrowness, how it's split.
I had 8 parameters in that, yes.
So one more stupid question. So we have seen the 2S and 2P, those are the subshells, right?
Yeah.
So
Yeah.
then what is 1/3 and 2/3? I mean, those normally there are like number of electrons in those subshells to create the doublet. So what is 1/3 and 2/3?
Well, now you're gonna have to take my modern business class. I'll turn to my
Yeah,
modern
here you go.
students
This one.
and ask them, what do those numbers mean? Explain to you, Oscar. Yes.
Like,
I'm a computer science.
Okay, what the-
I mean, you can look at Jeff if you want to, but he's not gonna.
The electrons they should be the superscript.
It has to do with the angular momentum.
Okay.
Like, so in the s orbital, it has no orbital angular momentum, but the electrons can have spin angular. When they transition to the p orbital, there's the spin orbital angular momentum and the spin angular momentum and the orbital angular momentum will either add together or subtract off from each other. That will create a small difference in the energy. And that's why we have it done.
Since
More.
you have this slide, Rajib, so that you get the frequency is normalized by the speed of light. In this one, right? So everything is
The
normalized.
velocity is normalized there by the speed in that
Yeah.
formula, yeah.
And then
That's just the Doppler formula.
the frequency is normalized by which frequency? Like here, the wavelength is normalized by the wavelength at rest.
So
New,
these wavelengths are normalized by these wavelengths. So this is the reference wavelength that goes into here, that's the rest wavelength. And then this array of wavelengths here is what goes in here. And that gets, and that's what transforms this axis into a velocity axis here.
but I mean like the new is the frequency, right?
No. It's not a nu. It's a V. Because it's
Oh.
velocity, right? That's what I'm getting here. Velocity.
Maybe
Nothing new.
Maybe
It's
you
all
need
old.
the lambda rest, it's the
Yeah.
wavelength that these emissions occur when you have something sitting still versus, and then you measure it when it's moving at several.
When it's
No, I get
typically, that will go down, right? The wavelength will go down and goes, right?
Depends which way, you gotta let me think, right?
Well, I thought like
It's
the
just a sign
left-hand
convention.
side, I thought the left hand side is the frequency divided by
Yeah,
the speed.
It's university, which is speed parameter,
If there is any analogy between black holes and hurricanes, like a geophysical holes, like the hurricane eye, if there is any somehow in terms of behavior. Like anything in a hurricane eye would be somehow trapped, would be hard to come back again.
Let's think about that. Those of you who got 243 from learn about hurricanes as Carnot engines. But yeah, obviously.
That's,
Anyone online?
so, I posed a question, I'll only comment online, just good presentation.
Oh.
But
Okay.
the, free to ask questions, I would say it's very different, the boundary, I think it's almost the opposite.
Yeah, I mean,
right?
there
So,
are gonna-
in a hurricane, once you cross into the eye, you're free to go in different directions, right? The forces at play don't really, I think it opens up, right?
I mean, there's also
Whereas when you
a
cross.
fundamental difference, which is that hurricane is on the surface of the earth. There's no surface of something that an accretion disk is sitting on.
An interesting thing.
right? So there's gonna be a lot of differences.
This is probably, I'm going in the opposite direction of all the questions that were just asked. What is a black hole? I looked it up on NASA and that was too wordy. As someone who has never seen even the Big Bang Theory, what is a black hole?
Alright, so black hole, the operating definition of a black hole is it's a region where gravity is so strong that the escape velocity is larger than the speed of light. So light can't escape because it's not going faster than the speed of light. The escape velocity is something that depends on how far you are from it. So as you get farther from it, there comes a point where, oh yeah, at this point, the escape velocity is the speed of light. And beyond that, it's less than the speed of light. So that's sort of the boundary that we think about what's called the event horizon of a black hole.
Why do you call it black hole? Why not blue hole or orange hole?
Well, if light's not coming out, what color is it?
Light's not.
Dark, there's no light.
If light is not coming out, then what color is it?
Dark is not coming out.
It's black.
Light is not coming out.
Right, that's not intended as any kind of a racial thing.
So,
What do we
question
already
from
know?
online.
I know they have many telescopes around in order to somehow reconstruct how the black holes look like.
So you're talking about the Event Horizon Telescope, which works in the sub-millimeter. So these are Herculean efforts to get the time on all of these telescopes simultaneously to do a campaign on just one object. They've only done two, right? They've only done M87, they've only done here. And so I was here to say, those are the two. Yeah. It's a massive event.
All right, let's thank Dr. Ganguly. And then if you are sticking around for the faculty mentorship, a faculty student mentorship session where we're going to talk about careers in astronomy, please hang out in here for that. Thank you.
All right, I'm gonna stop.
Get it? I hope eventually that I'm talking about.
So I also had thought we're using the next technology.
Oh,
Where we're off right here.
Yeah.